Have you ever stopped to think about what the quiet hum of an electric car and the slow, destructive creep of rust actually have in common? Well, it turns out they're two sides of the exact same incredibly powerful chemical coin. So let's dive into this hidden world of electron exchange.
Right, so that clean, quiet power that moves a vehicle like this, it's not magic. It is pure electrochemistry. It's about harnessing a very specific kind of reaction inside those batteries to get electrons flowing, creating electricity whenever you need it.
And then there's this. That very same fundamental process is what's behind corrosion, where metals just get slowly eaten away, trying to get back to their more natural lower energy states. So one process we desperately want, and the other, well, we're fighting it constantly.
So what's the real connection here? I mean, how can the same type of chemistry be the engine for cutting-edge tech and also one of the most common forms of decay? Well, the answer lies in this invisible dance of electrons.
It all comes down to something chemists call redox chemistry. Now, that's just short for reduction oxidation, and it's all about the transfer of electrons between different chemical species. This transfer is the engine driving so much of our world, from our own metabolism to the batteries in our phones. It's everywhere.
So the key here is how we keep track of this electron transfer. Officially, a redox reaction is any reaction where something called the oxidation number of an element changes. You can just think of this number as a kind of charge tracking system for atoms. It tells us who's gaining electrons and who's losing them.
And to really get a grip on these reactions, we first have to learn how to keep score. And in chemistry, we do that with these oxidation numbers. It's our way of figuring out who's winning and who's losing in this constant game of electron tug-of-war.
So what is an oxidation number? Well, it's basically a formal way of checking on an atom's electron situation. It's the hypothetical charge an atom would have if all of its bonds were 100% ionic. It's a really powerful bookkeeping tool for chemists to track everything. And the basic rules for this are actually pretty simple. First up, any pure element, like a copper wire or the oxygen gas in the air, has an oxidation number of 0. Easy. Second, for simple ions, it's just the ion's charge. And finally, and this is the important one, the numbers for all the atoms in a molecule have to add up to its total charge. Okay, so those are the rules for keeping score. But look, knowing the rules is one thing. Actually applying them is another. And this is where we get to the real challenge, the balancing act. Because while balancing equations is fundamental in chemistry, redox reactions, especially the ones happening in water, can be incredibly tricky to get right. And here is a perfect example of what I mean. On the left, you've got a simple reaction. You could probably balance that just by looking at it, right? But on the right, with the copper and nitric acid, things get messy. Atoms seem to appear and disappear, and it's all happening in water. Trying to balance that one by just guessing, yeah, it's pretty much impossible. So if we can't just eyeball it, there must be a better way, right? There has to be a system. How do chemists tackle these kinds of puzzles to guarantee they get the right answer every single time?
Well, they do. They use this really powerful and honestly elegant technique called the half reaction method. The whole idea is instead of trying to balance that entire complicated mess all at once, we just break the problem down into two smaller, much more manageable pieces.
And here is the recipe for it. I know, it looks like a lot of steps, but it is a completely logical process that just works every single time. The core idea is simple. Split the reaction into two, one for oxidation, one for reduction. We balance the main atoms, then use water and acid to sort out the oxygen and hydrogen. After that, we balance the charge with electrons, make sure the electrons match up, and then slam it all back together. Let's actually walk through it. Theory's great and all, but the best way to really understand this is to see it in action. So we're going to walk through two classic examples, one in an acidic solution and one in a basic solution, to see exactly how this recipe solves the puzzle. All right, let's tackle that complex reaction from before, solid copper reacting with nitric acid. Now, remember, this reaction is happening in an acidic solution, and that's going to be important for our balancing steps. Okay, first we split the reaction in two. The copper is losing electrons, so that's our oxidation half. The nitric acid is gaining them, so that's the reduction half. In this first step, we just make sure the main atoms, in this case copper and nitrogen, are balanced. And hey, they already are. Step one, done. Next up, we deal with the oxygen and hydrogen. In that reduction half reaction, we balance out the oxygen atoms by adding water molecules. But of course, now we've added hydrogen, so we have to balance that by adding H+ ions to the other side. You see the pattern? The copper half doesn't have any oxygen or hydrogen, so we just leave it alone for now.
Now for the really crucial part, balancing the charge using electrons. Notice that the copper reaction loses 2 electrons, but the nitrogen reaction gains 3. For this whole thing to work, the electrons lost must equal the electrons gained. So we find the lowest common multiple, which is 6. We multiply that top reaction by 3 and the bottom one by 2. And just like that, we have 6 electrons being transferred in each half. Perfect. And for the final step, we just add our 2 beautifully balanced half reactions together. The 6 electrons on each side, they just cancel out. And we're left with this, the perfectly balanced equation. Every single atom and the overall charge are now equal on both sides. The puzzle is solved.
But what if the reaction isn't in an acid? Let's try one in a basic solution. This just adds one extra, super simple step at the very end of our recipe. So we follow the exact same steps, 1 through 7, just like we did for the acidic solution. Once we do all that, we get this equation. But look closely. See that? There's a problem. We have an H+ ion, an acid, as a product. That simply cannot exist in a basic solution. So we need one final step to fix it. And this is the elegant final move for basic solutions. To get rid of that pesky H+, we add one hydroxide ion, OH-, to both sides of the equation. On the right side, that H+ and the OH- combine to form a good old water molecule. After we simplify the water molecules, we have our final correct answer. This really shows the power of the half reaction method, doesn't it? It is a systematic recipe that can solve any of these aqueous redox puzzles you throw at it, whether it's happening in acid or in a base. You know, this isn't just an academic exercise. From designing better batteries and more efficient fuel cells, to developing new medical sensors or preventing corrosion on a massive scale, understanding how to control this fundamental dance of electrons is absolutely key. Mastering this chemistry, it's the toolkit for building the future. The only question is, what will we build next?